Now, for the Dijkstra algorithm, we need to check if our current distance is less than the new node distance. So, if you recall, our new node are initialized with an infinity distance. So, we need to basically check if this distance is less than the new node dot distance. So the current node distance that by default is set to max value, but if we find a smaller distance, then we keep setting it to the lower distance. In this way, we're going to generate the best possible path. Okay, so at each pass, we set the distance if it's lower than the current distance. So if the distance is lower, then the new node dot distance will be equals to current distance, and the new node dot previous will be the current node. Because actually, if the distance that we just calculated is less than the old distance, then that means that our nearest neighbor of the neighbor node is actually my current node. So we set as previous in my new node the new neighbor, so my neighbor as the previous node, the node. And if you recall, in our matrix, in our ground matrix, we need to backtrack from the end to the start. So in this way, we are basically setting the previous to the node, and we are basically setting up our path for the Dijkstra algorithm. So we ended our for each, because now we've set it everything, and we need to say q.remove at 0. So we basically pop from the add. This is the same as q.pop 0 in Python for the BFS. But before ending this function, I need to say yield return new wait 4 seconds, and maybe we're going to try with 0.01 seconds. This will give us our coroutine, the time to sleep and then restart the cycle, and then sleep and then restart the cycle, and so on and so forth. So before ending, we need to backtrack. So this is the exploring part. So inside the while, so exploring the matrix. Now we need to backtrack in order to find the path. So backtrack order the path. Okay, so we simply say DFS from nodes from the destination position, so destination position.x and destination position.y to the start node, but we're going to specify it later, and we need to assign a material of path material. So now we implement this. So as we saw, the DFS can be implemented as recursive function, and we will exactly do that, but only after using the coroutine method, because as we said, we want to show the pathfinding process slowly. So like it wasn't distant. So we start a coroutine and we'll call it timed DFS. I know it's an awful name, please change it, but that's what my mind can think of right now. So destination and path material. Actually call it destination. Okay, so we start a coroutine and we implement the method with IA numerator. And that's really easy because as we saw, the DFS algorithm, it's pretty straightforward. So destination dot cell dot get component mesh renderer, and then material equals to path material. Then we basically sleep I'm gonna say like 0.01 again, and then we execute the DFS algorithm that in this case is really a single if that says destination dot previous is different, sorry, it's different from null. Then just do a DFS again with destination dot previous, because as we said, we just basically set the previous only if the distance is the lowest possible. So in the end node will be stored the previous, and the previous is basically our nearest neighbor, and then from the nearest neighbor we will have another nearest neighbor, and from this we basically reach the end. So we say destination to previous, comma, path material, and we're pretty much done. So we can save everything and gonna wait a second. Okay, we're gonna check which are the errors. Oh, actually, yeah, sorry. I forgot to update this thing. So what we need to add in the new node is initialization. Actually, we need the cell, the current position, and is wall. So basically, it's really easy because we have the cell. Actually, it's here. The current position, it's basically a new vector of int of y and x, y and x, because actually if you pay attention, this cycle is done in the opposite order. We consider in the matrix, sorry, we consider the x inverted instead of the y, because we consider these as our x and that as our y. Actually, it's a convention that I used, but usually in the matrix, you consider these as y's, and I'm considering it as x, and this as x. But yeah, I reversed it. So that wasn't my intention, but I implemented the code this way. So I hope it's not an issue. And then we say it's a wall. Yeah, well, true, because here we're checking if it's a wall. And instead here, we just say cell, the same thing basically. So false, it's not a wall. And then a new vector 2 of int of y and x. So we save it, and now we'll wait a second. Okay, so before running the code, we need to add the Pathfinder algorithm, and as you can see, we need to add all these materials. So let's be quick. Actually, I forgot to specify the start and the end node, because right now, as you can see, we're not calling the Pathfinder anywhere. So this algorithm is not called, so we need to call it actually, and we're gonna call it from here. We're just gonna get this dot get component Pathfinder, and we say dot Dijkstra algorithm. We pass the nodes, and the start position we will set new to int of 0 0. Well, actually, sorry, this should be out of the while. And our last position will be, let's say, new vector to int of y minus 1 and y minus 1 again. I'm just picking random positions. You can set the position in the bounds, but as you wish. So guys, a small correction, because I've made a mistake. Actually, this is not cell, it's actually new cell and new cell, because it should be a new object every single time. We cannot assign the material to the old game object cell that is a prefab. So that should fix the code that was broken. We wait a second and we run. Okay, and as you can see, we got our path finding algorithm. This is the Dijkstra algorithm, and actually we are finding right now the best possible path, or the optimal path inside the ground matrix. So if you want to double check or like do all of your experiments, you're just going to set it as y minus 1 and y is minus 2. And as you can see, we're finding another path. Actually, this path is different, as you can see, and yeah, now we may want to put some walls. So we're basically inserting like a bunch of ones, and this row is basically blocked. We may want to add another 0 here, and let's run the code again. So as you can see, we explore the matrix and we find the best possible path with backtracking. So that's all for today. I hope you enjoyed. Maybe this video will be split in half because it was quite long, but I hope you enjoyed. And if you didn't understand something, please leave me a comment or drop me an email. I'll try to answer as fast as I can. And up until next time, cheers.